you, Professor Tantillo, for this quite interesting and informative talk. Moving on to the Q&A. The first question, is there a transition state prior to the bifurcation after the MB model?
So no. So there is the ambimodal transition state. And then there's a second transition state that interconverts the products, but there is no transition state between them. So there is what's called a valley ridge inflection point. And so when you leave the region of the first transition structure, you're locally in a valley. There are walls on either side of you. Okay, and then as you fall down the potential energy surface, those walls start to go away, and at some point they go in the other direction, and then you're on a ridge, and you can fall off on either side. So there's a point called the valley ridge inflection point where that change occurs, but there is no other transition state.
Sure. Thank you for your response.
We'll leave that at that.
Were you saying something?
Nope, sorry, go ahead.
Oh, okay, thank you. So the next question, how can one prevent post-transition state bifurcation in a chemical reaction in order to enhance selectivity?
Right. So yeah, so I showed an example of this near the end with a solvent effect. So if you know there's a bifurcation, so there are two things you can imagine doing. One is to try to control the momentum that molecules have when they pass the transition state. That's really hard to do. The other thing you can imagine doing is trying to bias the potential energy surface towards one product or the other. And that you can do more rationally using classic, sort of Hammond postulate arguments. By pulling down the energy of one product or raising up the energy of the other, you ought to be able to tip the potential energy surface in one direction or the other. And that's essentially what happened in the rhodium case with the large catalyst, although it wasn't done by design, but that's really what that catalyst did.
Sure. Thank you for your response. Moving on to the next question. Why do most post-transition state bifurcations feature fragmentation products? And are there cases wherein stereoselectivity or regioselectivity in the reaction can be attributed to this phenomenon instead of different transition states?
So why are there? Yeah, so it's not particular to fragmentation. I just happened to show a case with fragmentation. In the it's so it yeah, it's hard to say that there's a certain type of reaction that will have a bifurcation. The ones that my group has looked at have largely involved carbocations. So even the rhodium reactions effectively are carbocation reactions because they are initiated by a hydride transfer that generates carbocation character. And carbocations tend to exist on pretty flat portions of potential energy surfaces. And flat surfaces means there's no barriers to things. So that's one kind of guiding principle, but there are other reactions like so-called bis pericyclic reactions that are really different, that don't fit into that mold. So I would say there isn't a specific type of reaction that you expect to have a bifurcation. I would say if you're adding something to a pie system, like adding to the so even like I hesitate to say this, but we teach students about halogenation of alkenes in undergrad organic chemistry. There's a bifurcation there. When you add a halogen to an alkene and then the halogen picks one side or the other, there's a bifurcation. So adding to a pi system, almost always the electrophile comes in towards the middle and then has to pick a side, which leads to a bifurcation. So there are some cases where you can kind of guess there might be a bifurcation, but it's not super general.
Sure. Thank you. In the case of a PTSP, what and how significant is the role of entropic effects in determining which product is favored?
Yeah, that's a great question. I stay up at night not sleeping, worrying about entropy. Yeah, so you're effectively considering entropy when you run dynamics because you're doing a whole bunch of different configurations. so, but it's hard to sort of parse that out into a simple number. For example, there are people like Zhongyue Yang at Vanderbilt who have looked at that explicitly. So another thing it took me a long time to realize this, but entropy is also related to sort of the width of a pathway. So sort of the flatter your surface, the better the entropy. And so that, if you have a good picture of the potential energy surface, which is hard to get, you can get some insight into that as well. And then sometimes in these cases, there are what are called entropic intermediates, where there might not be an intermediate on the potential energy surface. But if you account for entropy, there might be a shallow intermediate. And so it might not it might be a bifurcation in potential energy, but not in free energy. There might be small barriers to make the two products in terms of free energy. That you can usually see when you do trajectories, because the trajectories get stuck and they hang around in that region for a long time rather than going right to the products. So entropy is always important. And it's generally hard for organic chemists like me. I'm a trained organic chemist, to wrap our heads around entropy, and I'm still struggling to do that and want to be able to do that in a way that I can use entropy for design. We've been conditioned to, design things based on enthalpy, add a hydrogen bond, remove a steric effect. Those are we think about those in terms of enthalpy, although there's entropy parts of those as well. I want to rationally use entropy more often, and so I'm still struggling with that. It's a great question.
Sure, thank you. So the next question: what role do the orbital orientations in the transition state play in product selectivity?
Say that one again.
What role do the orbital orientations
Oh, yes.
Play in the transition state and for product selectivity?
Yep. So orbital alignment always important. So there's nothing different here than in any other context, except that the geometries along trajectories, instead of having one pathway and one transition structure, you're going through the region of the transition state in slightly different geometries, where the orbital alignments will all be slightly different. And so that could, if you're at the point where you get to the ridge, you pass the valley ridge inflection point, and you're at the point of the ridge where you have to pick a side of one product. You have the momentum, but in addition, an orbital interaction can be the thing that pulls you to one side or the other. And in fact, I had a visiting student from India who was looking at that for a specific bifurcation. Can we manipulate bifurcations using specific donor acceptor orbital interactions, which is really amounting to modifying the potential energy surface on each side of the bifurcation. So orbital interactions, still important, always important. Don't forget about orbitals.
Yeah, thank you for your response. Moving on to the final question for the day. Can you generalize a few common features of the catalyst that you have studied that can inhibit post-transition state bifurcations?
Yeah, so for us, for catalysts, we've mostly looked at dirodium tetracarboxylates, and we've looked at not just CH insertion, but cyclopropionation cope reactions, and we started to look a little bit at other reactions that generate carbines. So in ours specifically, it's been those kind of catalysts, and I just wrote an accounts of chemical research paper on all of that, which will be out any day now. I have the proofs next to me. But I don't want to give the impression that that's the only kind of catalyst system where you could have a bifurcation. We've also looked at, as I mentioned, a lot of carbocation reactions that happen in biosynthesis, and there the catalysts are terpene synthase enzymes, which are very different than dirodium tetracarboxylates. So I think that the bifurcation, what I will say is, I think the bifurcation tends to be a result, in my experience anyway, more of the inherent reactivity of the substrate, and then it's modulated by the catalyst. So the catalyst can control which side is preferred and by how much. But it tends to be more the reactivity of the substrate. The carbocation tends to want to bifurcate, or the carbene tends to want to bifurcate, rather than the catalyst itself forcing a bifurcation on something. It tends to be more controlling the selectivity of a substrate that will bifurcate. But I can't say that that's a complete generalization. But that's my impression and gut feeling at this point.
Thank you so much, Professor Tantillo, for the detailed explanations.
So I would request you to put on some concluding remarks for our audience.
Yeah, I just want to say thank you, and I'll point out that these are some of the best questions I've ever gotten on this work. So I congratulate the audience thank you for paying attention. I appreciate it. And your questions were very deep questions, and I will go home and think about them more myself, and maybe study some more systems based on your questions. So thanks again.
Thank you so much, Professor Tantillo. So this brings us to the end of today's session. We hope that you enjoyed this broadcast, and we invite you to view the edited recordings from the past events, as well as this recording from the ACS Science Talks library. You'll soon receive your certificate of participation along with a survey form on your experience about the ACS Science Talks. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy. And thank you so much again, Professor Tantillo, for joining us. And it was indeed a very great lecture. Thank you so much. Thank you all.